Okay, the Federal Center for Disease Control has determined that the average height for an American male is 5 foot 9 inches tall. So the Federal Center for Disease Control, 5 foot 9 inches tall. Suppose I select 1,000 people randomly from our country, and these are American males. This is the population mean for American males. Suppose I select 1,000 people from our nation randomly, and I measure their heights, and my average is 62 inches. Well, what I just did here is I made a point estimate. I created a point estimate from my sample of 1,000 people. So my point estimate for the average height of American males is 5 foot 2 inches. Now you all have knowledge about this, and you recognize that, well, what I must have done here was somehow, if this is what our population looks like, a plot of our population distribution, and the mean down here is 5 foot 9 inches for our population distribution. Well, when I pulled people, I must have pulled more people from this side of the curve. So my average would have been lower. And you recall when we did the dice problem and you guys rolled 2 dice and you took your averages, sometimes your average was below the mean, sometimes it was above the mean. Very rarely was it exactly the mean. So there's issues with point estimates. People will often take point estimates and try to make inferences about a population. And it's really not a very solid way to go, because as we all know now, the sample means can fall, although they'll fall in a situation that resembles a normal curve, according to the central limit theorem, they will not necessarily be exactly representative of the mean. So you can only go so far with point estimates. For that reason, we, in statistics, have decided to use something called, well, this is actually just another approach, an interval estimate. So we take the information that we collected, this information here, in our sample, and we use it to make an interval prediction to some confidence of our population. So, for example, we might make a statement that ultimately, after we've done the analysis, we might make the statement that we're 95% confident that the mean is between these two values, A and B. So how might we set something like that up? Well, consider this. Think of a normal curve where we're concerned with this area between 2 points, and it is made up of 95% of the data falls in this area. 95% of the data falls in this area. So, of course, that means 5% of the data falls outside the area between these 2 points. Let's say this is Z1 and Z2. I guess this is I'm showing this as a standard normal curve. So, if 5% of the area falls outside of it, then on this tail, there's going to be 0.025. And on this tail, there's going to be 0.025. Where this represents 0.95. So I'm writing this in decimal, and these are also in decimal to go with this. So 5%, that means 2.5% over here, 2.5% over here. Okay, so if you go to your tables and you have a situation like this, you can figure out that z then. Well, let me actually draw it for you to show you what I'd want you to actually look at if you're going to do this. So you go to your z table, for example, and you could look here and you could figure out what this z is when you have 0.025 here. That means this area, including this tail, because that's how you're going to calculate your z, is going to be 0.975. So if you go to the body of your z table and you look at 0.975, you can back calculate what z is, and z turns out to be 1.96. So for a situation, so if this z is 1.96, then if you just figure out what the z is for a situation where you have 0.025, this is going to be minus 1.96, because we know that the mean here is 0 in a standard normal curve. Okay, but z, we know, when dealing with sample means, is x bar minus mu over sigma over square root of n. So we're going to set ourselves up an interval, what we call a confidence interval, based on this idea. So if that's the case, then I can say that minus 1.96 is less than z is less than 1.96, right? Because this z's in here somewhere. It's going to be between minus 1.96 and 1.96. If I replace z now with my equation for z, we've got x bar minus mu over sigma over square root of n is less than 1.96 minus 1.96. Now I'm going to do some algebra, and it's going to be algebra involving inequalities, so you might have to review if you want to follow exactly what I do here. So the first thing I'm going to do, I'm going to multiply both sides by sigma over square root of n. So I'm going to get 1.96 times sigma over square root of n. That means that when I do that, this sigma over square root of n in the middle here is going to be sigma over square root of n divided by sigma over square root of n, or 1. So this is going to turn into x bar minus mu is less than 1.96. If I multiply this side by it, I have to multiply this side, and I have to multiply this side. So I still have to multiply this side by sigma over square root of n. Okay? All right, let's isolate this mu in here. So I'm going to subtract out an x bar. So I've got 1.96 times sigma over square root of n minus x bar is less than negative mu is less than 1.96 times sigma over square root of n minus x bar. So I subtract x bar in the center here. That drops this x bar out, but then I have to subtract x bar off on both of these tails here. Okay? Now, I want this inequality to be nested around the population mean, mu, and I want this to be positive. So what I have to do is multiply by negative 1. And when I do that, what happens is this becomes mu now. But what will happen here, so if I multiply this by times minus 1, I have to multiply this by minus 1, and I have to multiply this by minus 1. But the thing is whenever you multiply or divide by a -1 and you're dealing with inequalities, you have to do what? You have to flip the sign. So now my inequality sign flips when I do this. And this is going to be over here x bar minus 1.96 times sigma over square root of n. And over here, minus 1 times minus this is going to be positive. And this is going to be positive, so this is going to turn out to be x bar plus 1.96 sigma over square root of n. And that makes sense. It all makes sense. Probably a better way to write this. Usually we see this written with the lower value on the left and the higher value on the right. So I'm just going to do that. So I'm going to go x bar minus 1.96 times sigma over square root of n is less than, our population mean is less than x bar minus 1.96 times sigma over square root of n plus 1.96. That's this one here. So this number is bigger than this number, and our mean is nested in between that. Well, this is a confidence interval. And this is actually turns out to be, since we're looking at 95% of the curve, a 95% confidence interval. Notice we used information, this guy, our mean here, and the n here from our sample. But we also combine that with this sigma because remember we had to make this correction. We use this from our population. So that's a population term. That's a sample term. So 1,000 goes in there. A 5 foot 2 inches goes in there. So kind of what we're saying is 5 feet 2 inches minus 1.96 times sigma. Now I didn't give the population standard deviation, so I'm just going to leave it as sigma divided by square root of 1,000 because I had 1,000. I had 1,000 people in my sample set. Is less than our mean, is less than 5.2 inches, 5 foot 2 inches, plus 1.96 times sigma over square root of 1,000. So this is our 95% confidence interval. This over here is, and you've probably seen this on TV when you see results, this is our margin of error. The numbers are going to be the same. The absolute value of these numbers will be the same. Margin of error. So let me finish up here. Running out of time. In general, I could write this as a general confidence interval where we need to figure out what x bar minus z, and we'll call this alpha over 2, and I'll talk about that a little later, sigma over square root of n, because I just don't have time in this one. I have to save it for the next video. It's less than the population mean is less than our sample mean plus sigma over square root of n times z subscript alpha over 2. So this is what you need to learn and use. Okay, so I'm gonna end it here.